the drunkard. We're trying to convert the problem about the drunkard into this setup of rewards and states. And so there's a lot of different problems you can convert, and then you can try to solve them with the Bellman equation. You just got to make sure you do the R vector correctly. Actually, the one question that you guys should be familiar with now is the question from the homework, question 2b, which was probably the hardest question of how many times do you reincarnate? I saw some pretty clever solutions that were also correct, but one simple way is to set up exactly this equation with the correct R vector. I guess I'll post the solutions or talk about them in class at some point. So it's another situation where if you just think of what is the right R vector, then it's a snap with this kind of equation. Okay, in any case, what is the answer here? Let's see what you guys said. Reveal counts. All right, we got 11 people saying 0, 0, 0, 0, 0, 1. All zeros except the last entry is 1. 11 people said that out of 14, so pretty big majority. Let me reveal that that's the wrong answer. This is the wrong answer. The thing that 11 out of 14 people picked is wrong, not correct. If you do that, you will get something else. In fact, if you do this, things will explode. If you do value iteration, remember, value iteration is like hitting cosine on your calculator over and over again. If you hit cosine on your calculator over and over again, it converges to the number. The value iteration works. If you hit e to the x over and over again on your calculator, it will not converge. It will blow up to infinity. And so if you do this 0, 0, 0, 1, like you guys suggested, this will not converge. It will blow up to infinity. You're doing something else. So let's reopen it. This is a great question because I think it means we're fundamentally mixing something up. I'm going to reopen it again for a vote. Maybe, is this a question? Yeah, question. Yeah, go ahead.
Because you can't have like a non-zero entry at a terminal state in the reward vector.
That is true. So yeah, if you have in Snakes and Ladders, for example, if you did a reward vector of a 1 in the end in Snakes and Ladders, that would count how many times were you in the final square in Snakes and Ladders. And as you know, in Snakes and Ladders, you eventually end up in the final square, and then you spend eternity there. So you will be adding on 1, 1, 1, 1, 1 for all the eternity you spend in the final square. So it will blow up to infinity. So yeah, that one will blow up. That's not the right thing. And in fact, what you guys have done is made a very common mix-up of two different concepts. But I will let you guys revote. Please chat with your neighbors, try to figure out what's going on, and we'll take it up in just a few minutes. So I'm going to reopen it. Feel free to go chat, and I'll see you guys in a couple minutes. Okay, it's open again. You have to put your answer in. Even if you want to stay on the same answer, you need to put your answer in again. And let me give you 2 minutes to see if we can get it. Okay. Time is up on round 2. Excuse me. Let's see what you guys said this time. Did a lot of people, is there a consensus? All right. Now 13 people are in 0, 1, 1, 1, 1, 1, 0. All ones except for the first and last entry are 0. One brave soul is in all zeros, all by themselves. What is the correct answer? The correct answer is the brave soul got it. It is all zeros. So the brave person here got it all zeros. What you guys are doing, I think you're mixing up various problems. So let's go over it and have like a nice little review here. I think we're mixing up what this R vector is. And it is exactly what we left off on last class. Terminal versus ongoing rewards. All right. So this is the thing. So let's review the baby Bellman equation. And the equation is exactly the one I wrote on the board. V equals R plus M times V. Where R, I think this is the thing that maybe you guys were forgetting. R is the rewards, the one-time rewards at state S, given, say, S0 equals S. So, okay, it's a vector. Its S component is that. So I'll just say reward, maybe not reward of S. Okay, so when you are at a certain state, you will jump to somewhere and you get a reward. And R is the expected value of the reward. For example, and this is the example we've done a lot of times. Example, if the reward equals 1 at all non-terminal states, and the reward equals 0 at every terminal state. So this is the situation we did in snakes and ladders. We said, let's make a reward of 1 at all the non-terminal states, not snakes, and the reward 0 at every terminal state. So this was R equals, and it's a column vector, 0, 1, 1, 1, 1, 1, 0. That's the vector. Then the total return, which is the sum of all the rewards. So this is G, which is the sum of all rewards. Let's call them rewards sub t, t going from 0 to infinity. That will be equal to n, which is the number of steps until a terminal state. So this was the main example we did in class. And I think a lot of people maybe were confused on where this vector 0, 1, 1, 1, 1, 1, 0, where does that come from? But it's counting. You get a reward of 1 every time you step on a non-terminal state. So what is the sum of all the rewards you get? That's the total return. The sum of all the rewards is just counting how many times did you step on a non-terminal state. Another example, let's just do the example from the homework. Another example, in the homework, we wanted the number of reincarnations. And one way to do this problem, so this is in homework question 2. The number of reincarnations, that's equal to the number of steps on square 0 minus 1. So a lot of people notice that. And the reason it's minus 1 is because you start the game on square 0. Even if you exit the game immediately and have 0 reincarnations, you still have 1 step on square 0. And therefore, you can write this as the number of steps on square 0 on square 0. This is the total return G when R equals 1, 0, 0, 0, 0, 0, 0, i.e. the reward is 1 for square 0 and 0 otherwise. So all the other rewards are 0. Okay, so that was the sort of solution to question 2, I guess question 2b. So that's how a lot of people solved it. It really is the value function with this reward vector R, which has a 1 in the first component and 0s everywhere else. So this vector R, it is the rewards, and I think even more specifically, so you don't get mixed up, you could think of R is the ongoing rewards. R equals ongoing rewards. So every time you step on something, you get a reward, and the reward vector tells you how much reward you get on average for each state. So how much reward do you get when you're in state 0? How much reward do you get in state 1? And the value function is the total returns, the sum of all the rewards. Okay, so that's a bit of a review. R is the ongoing rewards. And so if you put in this vector of 0, 1, 1, 1, 1, 0, you will count the total number of steps, which is something interesting you could ask about the drunkard, right? So going back to the answer over here, right? That is a question you could ask, is like, how long until he either gets home or falls off? Like, how long is his night going to be before it ends? Interesting question, but it's not the question we're asking here, right? So here we're asking, what is the chance that he gets home? So if you put in r equals 0, 1, 1, 1, 0, you get the answer to a different question. That's not what we want. So it turns out what we want is this one with all zeros. And I'll explain exactly why in a second, but any questions or comments about so far? What does the vector r represent? And this was partially why question 2b was supposed to like get you involved and try to like intuit what it was. I think some people got it, and some people maybe like figured it out without really understanding. Either way, any questions? Okay. Now here is the thing that might bother you. I'm telling you the answer is all zeros. And that's because, if you step on a certain square, however times, it doesn't help you get home or not, right? Like stepping here or stepping there doesn't help you get home. Well, I guess here's another remark that we can also answer, which was a question. Remark, which is that R of S, let's call it S terminal, the reward of S terminal of this R vector, the ongoing reward, must be 0, or else the total return goes to infinity. That was the remark we made earlier. Right? So if it was non-zero, then when you're at that terminal state, you would keep adding it up over and over again. These ongoing rewards would add up to infinity, and then the value function wouldn't make any sense. It would be something that is infinite. I will say you can also fix this by making the discount factor gamma less than 1. But we're mostly in this course going to look at gamma equals 1, so don't worry about that. Okay. So I'm telling you the right answer here is going to be, the rewards will be, the ongoing rewards will be all zeros, 0, 0, 0, 0. And that's because, it doesn't matter how many times you step on the square x. What matters is, did you get home or did you fall off the cliff? Now, one thing that might bother you mathematically, if you look at this equation and r is 0, then we're not adding anything on, right? And before we said it's like this infinite sum involving r. If r is 0, isn't this just going to be 0? And that should bother you. And that's the next question is, wait a sec. If r is all zeros, then wouldn't the v vector just be all zeros too? Like, how is it going to be something that's not 0? What's going on here? So how could it be that the right answer is to have an r vector which is all zeros? Wouldn't that always just lead to the v vector, which is the value function that we're looking for? We're trying to solve for this v. Wouldn't that also come out to all zeros? And of course, it doesn't come out to all zeros. There's one key thing I'm missing, and that's what I want you to answer in here. So think about, what is the thing that I'm missing, and why do we need it? Okay, I'll give you a few minutes to think. Okay, there's like 30 seconds left. I guess only like half the people have answered. Feel free to put in an IDK if you really don't know, or you can take a guess. Any kind of guess is always good. All right, let's see. What did we get to? Where's the mouse? Okay. Okay, 15 answers. But how many people are there? 3, 6, 9. 3, 6, 9, 12. There's only 13 people in the room and we have 15 answers. Okay. This is a good lesson. Okay, let's see what people said. Reveal counts. Ooh, nice word cloud. Okay. Because. I like the word because. All right, what's the because why? All right, I don't know. Very good. Is it because R is the average reward vector? So it turns out the value function that we're looking for, right? What is the thing we're trying to look for? The V we're looking for, the value function, also only cares about averages. So recall V of S, so V at some state S, the value function, it is the expected total return, that's the value of G, the total return G, given S0 equals S. So you start at state S and you ask, what is the value of, on average, all of the total rewards? And because V only cares about averages, you will only ever see the rewards in their average form, right? So, like a situation where you get 1 point at every location, or a situation where you get 2 points half the time at every location, are identical from the point of view of V. So it's true that we only care about averages, but it doesn't save us, right? If R is on average 0, shouldn't V also be on average 0? Like, why would it not be on average 0? So great comment there. Maybe it's something to do with the averages, but that's not what it is. Yeah, because the reward and the value are different. Yeah, this is true. So somehow V is going to end up being non-zero, even though the reward, and again, it's very like reward can mean a lot of things, right? So just be careful with the language. Like when someone says reward, first of all, they might actually be talking about the total reward, which is what we call the return. They might be talking about the reward at one state S, which is the vector R, or they might be talking about something else. And that's really the confusion. So like this R vector has a specific meaning, and I've written it out here. And V has a specific meaning, and I've written it out here. And there's one sort of ingredient that is missing so far. Okay. Something with the transition matrix. This is not right. The transition matrix isn't there. Yes, because math, I don't know. I kind of feel like we model the things, we set things up, and then the math like solves it. But it's really how are we setting things up? All right. Response number 7 says specifying the value of V at the terminal states by hard coding V of 0 equals 0 and V of n equals 1. That is a perfectly correct answer. There is one other sort of secret keyword that I'm looking for here. Let's see if this has the super secret keyword. Super secret keyword. Okay, the other keyword. So this is exactly 100% correct. And the keyword I would say is these are terminal rewards. So it's about the terminal states. And V of n equals 1 is kind of a terminal reward. It's a one-time reward that you get at the terminal state. And so this is the thing that is missing. This is the thing that is missing. So this is important. Ongoing versus ongoing rewards. Ongoing rewards. That's the R vector versus terminal rewards. Terminal rewards. So ongoing rewards, you get them over and over again. If you step on the state, every time you step on it, you get rewards from the vector R. But the terminal rewards are like one-time bonuses. You get exactly one time. And they are hard-coded into V, into values of V at terminal states. At terminal states. And in this particular problem, the way we are going to do it is we're going to hard code in the value V of 0 equals 0 and V of n equals 1. So this is for the gambler's ruin. The drunkard's walk. The drunkard's walk. We have V of 0 equals 0 and V of n equals n. And if you remember, actually, in our equation, the equation does not specify what v of 0 equals 0 and v of n are. Right? Like the equation v equals r plus mv. This equation, because the r vector is 0 at the terminal states, this is undefined. So you need some kind of equation like this. You need these terminal values to have solutions at all. If you don't specify something like this at the terminal values, there will be infinitely many solutions to this equation. If you want to nail down one equation, you need both the equation and the terminal states. Yeah?
Instead of having multiple terminal states at a terminal class, would we only need to set the value of one to be one in one set of the class or include every single class?
So what's a terminal class?
As in like a class that once you went there, you're always setting that class and can be those.
Yeah, okay. So far, every example we've done has at least one terminal state. And so the Markov chain eventually reaches the terminal state and then it's stuck there forever. It is true, you can have Markov chains where they go on forever. So they have 0 terminal states. I guess in your what you're saying is like take the set of things that you eventually end up in and you kind of like cycle between them. So in that situation, there's 2 things you can do. One is you can make the gamma less than 1, and then you can make these infinite sums finite. Or you need to make sure that the r is equal to 0 at every single vector in the terminal class that you call it. And then you still need to specify the values in the terminal class. So yeah, we're not quite doing that, but it's true like this thing unchecked will explode in that situation. Yeah. For now, I do want you to think of them having terminal states. It's a little bit more straightforward. Great question. All right, so this is the part we need. These are kind of like boundary conditions. If you've taken a class on differential equations, what this should remind you of is this is like the equation, or like the differential equation, or the difference equation, which tells you how does, it tells you like how does the function relate to itself? How does the unknown v, how is it related to itself? And these are the boundary conditions, and you need both together to be able to solve something. If you don't have the boundary conditions on its own, there's more than one solution to the equation. You need both. And the interpretation of these values are these are the terminal rewards. So they are the one-time reward you get when you get home or if you fall off the cliff. And in our situation, we're saying, look, we're going to give you 1 life point if you get home. We're going to give you 0 life points if you fall off the cliff. And the value function v is the average of the total number of life points you have. Question, yeah?
Would it matter if we set 0 to -1 instead of 0?
You could say you get -1 life point if you fall off the cliff, and then you get +1 life point if you survive. And then you would find the average of the life points you have, with an average of 0 meaning you get -1 half the time and you get +1 half the time. If you do it this way, then the interpretation is that it's the probability. So that's why I'm doing it this way. Of course, you can set it up however you want. So v of x is the expected value of the total reward. The total reward. I should say return. So total reward and return mean the same thing. I'm going to try to add extra adjectives to make it more unambiguous, but we'll see. So it's the total return given you start at x. And in this situation, the ongoing rewards are 0. So since r equals 0, you get no ongoing rewards ever. And the only reward you can get is the terminal reward at the house. And v of n equals 1 is the only terminal reward. It's the only terminal reward. Then what is the total return? Well, the total return, it's 1 if you make it to the house, and it's 0 otherwise. So this is the expected value of the indicator function of you made it to the house before the cliff. House before the cliff. Right? Because if you make it to the house, you get one point, and you're happy. If you make it to the cliff, then you get 0 points, and then you're stuck at the cliff forever. You never get any other points. And what is the average value of something that's either 1 or 0? It's the probability that it happens. So it's the probability. This is the probability that you make it to the house. To the house before the cliff. Given your starting position. Okay. So that is the secret, is that these sort of endpoints, they encode the terminal rewards, And the total return is a sum of two things. It's the ongoing rewards you get for the whole episode, plus whatever you got, the one-time values at the end. And by setting it up correctly with a 0 and a 1, we can solve our problem. Okay. Questions or comments about this setup? Yeah?
So how this is different than the eigenvalue eigenvector equation?
It's very related to an eigenvector eigenvalue equation. So that's true. So we're solving v equals mv subject to v of 0 equals 0 and v of n equals 1, right? So v equals mv, this is the set of all the eigenvalues or all the eigenvectors of eigenvalue 1. And we're finding the right linear combination of all the eigenvalues, all the eigenvectors of eigenvalue 1 that satisfy these two equations. Okay. And the number of, the dimension of the eigenspace is always the number of terminal states plus 1. So again, this is the hard theorem that I mentioned last class, the Perron-Frobenius theorem. It says that the dimension of the eigenspace, it's equal to the number of terminal states plus 1. And the plus 1 is actually, there's always a very silly v that you can add, which is the constant v. So v equals 1, let's make it 1. Let's make it c. C is always an eigenvector. So that's always an eigenvector. And basically, we got to find the right combination of eigenvectors that satisfy this equation. Now that I'm looking at this, maybe it's not plus 1. If the number of terminal states is 0, it's supposed to be 1. And then if the number of terminal states is 1, then I guess... Okay, I think it's correct this way. I'm not 100% sure. I wasn't planning on talking about this. Okay, yeah, you guys can look it up later and tell me if it's wrong. But this is, okay, this like plus c, this is like the same way when you have a differential equation. Very often, plus c is like another solution. All right. Okay, great question, yeah. So we're essentially, we're finding eigenvalues, or eigenvectors, but we're finding the right eigenvector that does what we want. Great question. Anyone else? Okay, so now let's make the computer do it, right? So up until now, we have only looked at problems, like your homework had only had problems without any terminal rewards, right? Like so far in snakes and ladders, we said, oh, we have these ongoing rewards and there's no terminal rewards. And you kind of make, if you make it 0, if you always say it's 0, that's saying there's no terminal rewards. So the new thing in this problem is this like 1 over here, which is terminal reward. When you get to the house, you get 1 point. And that's what kind of makes it different than what we've done before. But the same kind of stuff works. Same kind of infinite sums or value iteration will work to solve it. You just have to have the right boundary values for v that are now non-zero. All right, let's do it on the computer now. And so we were doing this last class. Okay, I have the solutions over here, but let me pretend I don't have the solutions. And let me start from scratch. We might get to this video later. Okay.
So was it Perron-Frobenius, or what was
The
that?
Perron-Frobenius theorem. Perron, yes.
No, it's the Fro part that I'm trying to...
Oh, Frobenius. Okay, yes. I might have spelt it wrong. Let's try again. Frobenius.
Okay.
Maybe there's an E here? Question mark? I don't know.
It's F-O-B.
Okay, great.
Unless it's another one.
No, and there's only one Frobenius. Some German guy. Okay, anyway. All right, let's do this. So let's make a new notebook. By the way, please let me know if you can't like see it, if the font size is too small or something. I'm happy to slow down or make it bigger or smaller or whatever you guys need. Oh, and yeah, and somebody suggested I can make it full screen. Let me try making it full screen.
I think you just gotta click the up arrow next to Gemini.
Yeah, that's one thing I can do. Okay, that's helpful. And then I think there's some way I could do like view, enter full screen. And it gets even bigger. Okay, yeah, let's do that. Okay, so what do we got an n, which is the number of states. So let's say n equals 10. Actually, it's the number of states plus 1, right? N is the location of the house. So this is the location of the house. And we have an x, let's call it x init. This is, let's say 3. This is the initial location of the dude. And we're going to make all our usual things. So we're going to start by making a matrix M, which is np.zeros of n plus 1 by n plus 1, just like in the homework. And now we got to fill in the M with the rules that you go left and right with probability 50%. And one way to do it is a for loop. But again, I want to show you the slightly smarter way is to think of the, let's say, like non-terminal states, which will be np.arange from 1 to n. And that will be a vector that has the numbers 1, 2, 3, 4, 5, 6, 7, all the way up to n minus 1. So I put an n here. N does not include n, so it's n minus 1 plus 1. Yeah, why don't we print out the non-terminal states to make sure I'm understanding it correctly. Yeah, so it's 1 to 9. And so a very easy way to fill in the matrix M is you can put an M of non-terminal states. So going from a non-terminal state to the non-terminal state plus 1, that should have 50% probability. So what this is saying is, in the matrix M, when you start in the non-terminal state and you go to the same one plus 1, that's 50%. And by doing it, I have actually changed the value of M on 9 different locations. So this is a lot faster than a for loop. And as we get to harder and harder problems, this kind of thing becomes important because for loops become slow. So if I look at M, you see it's got this 50% on the super diagonal, right? So starting from, say, state 1, you go to state 2 with probability 50%. And then I similarly want to do that the other way. So stepping left, stepping down 1 should also have 50% probability. Okay, and so now the matrix M looks like this. Very nice matrix. Does anyone see what I'm forgetting in the matrix M that I need to put in? Otherwise, everything will break. Yeah.
1, 1.
Yeah, that's right. You need to put a 1 and a 1 here. You could, again, in this case, there's only 2, so it's not so bad. But you could also do like terminal states, and that would be np.array of 0 and n, right? So 0 and n are the terminal states. And then I could specify that m of terminal state, comma terminal state equals 1. So if you start at terminal state, you will go to the terminal state with probability 100%. And there we go. And then now it should be all good. So that's the matrix we had last class. And now we're going to try to solve our equation. I guess let's write the reward vector. It's going to be 0, but this is the reward vector. So I'll call this rewards. Let's call it ongoing so we don't forget. And that's np.zeros. Actually, let's make it 1s. And then I will make sure it's 0 by multiplying it by 0. And then we can change it later. That's the R vector from the warm-up question today. And then finally, I have the value function, the V, the value function. And this is unknown. This is what we're trying to solve for. And why don't we start it at all zeros, and then we can iterate. So we start it at all zeros. Here is the very important thing. You got to make sure to hard code in the 2 terminal rewards at 0 and at n. So let's make sure the value function at 0 equals 0, and the value function at n equals 1.0. This is hard code in the terminal rewards. This is super important. If you don't do this, then it's like having the wrong R vector, right? If you even have the right ongoing rewards, if you have the wrong terminal rewards, nothing will work. Okay, so now it's all set up. We just do value iteration. So to do value iteration, we take some number of iterations, say 10, and then we loop over it for iter in range num iters, and we just apply it to itself over and over again. So the value function will be the rewards ongoing plus m at value function. Okay, and again, it's kind of funny because in math, right? We say like v equals r plus mv. That is an equation that we're trying to solve. And in computers, we also write down v equals r plus mv, but it means something different, right? When you write on a computer, when you say v equals r plus mv, you say set the value of v to what r plus mv is. And so it's like pressing the cosine button over and over again. But if we do this, this should work, and we should get closer and closer to the real thing. To show you what it looks like, let me plot it, and instead of plotting it live, let me copy and paste the plotting code. I think I got the plotting code from ChatGPT anyway. So ChatGPT is great for this kind of stuff. So it's this plot. You have to tell it what plot is. In this case, plot is matplotlib.pyplot. This is the plotting thing that everyone uses. Okay, so now if I do this, it should draw these things for us. What am I missing? Okay. Okay. V is not found. Right, value function. Value function. A value function. Okay, so why did it start at something non-zero? Oh, let me rerun it. Okay. So here's the plot, and we can sort of see what it's doing. So at iteration 0, we start with our guess. We think the value function is all zeros, except for the terminal state is 1. And then as you apply more and more iterations, you're sort of getting closer and closer. The value function is getting closer and closer to the true answer, the true value function we're looking for. So after one iteration, it looks like this. I guess let me. So it's saying if you start in state 9, you have a 50% chance of surviving and getting to your house. That's because if you start in state 9, you have, in one step, you have a 50% chance to get to your house. In state 8, it still thinks it's a 0% chance. But as we apply more and more iterations, these probabilities are all going up. And by iteration 4, we think it's like a, what is it? Like a 75% chance that you'll survive from state 9. That's because you can either get there right away, or you can like go left and then come back. So state 9 becomes more and more valuable. And then as we go on, the value functions sort of slowly rise. Let's do it like 100 of these. So they're going up, and they're getting closer and closer to, this is what it's kind of converging to. So just like when you press cosine on your calculator, eventually it sort of stops changing. Here, all these iterations, 95 to 99, look exactly the same in our plot, and that is the right answer. That is the solution to the Bellman equation, and it is the solution to our problem of how many, what's the probability you live as a function of where you start, right? So where you start is on the x-axis, and on the value, in this case, is equal exactly to the probability that you survive, and it's this nice looking function. Question over here? You might notice a special feature of this function. Does anyone have a guess of what function this actually is? Yeah. What is it? It's a staircase?
Stage overhead.
So what? Yeah. Let's say what's the formula? What do you think is the formula in that case? So, let's write this down. The by value iteration. The solution. The solution looks like. So it's v of x equals what? What is the chance if you start at position x? What is the chance of you surviving? Can anyone guess what the formula is? Yeah. X over n. Yes. X over n. And you can check by hand. In this particular case, we can verify this is the solution. How can we verify that it is a solution? We plug it into the Bellman equation and we see, does it satisfy everything? So the Bellman equation in this case says v of x has to be equal to, so the Bellman equation says v of x has to be equal to 50% times v of x plus 1 plus 50% of v of x minus 1. Let's see, is that true? So the left-hand side we think is x over n. What is the right-hand side? It is 50% times x plus 1 over n plus 50% times x minus 1 over n. So we're plugging in our guess, and we're going to see if the left-hand side equals the right-hand side. And if you simplify this, you expand it out, you have 50% times x over n plus 50% times 1 over n plus 50% times x over n minus 50% times 1 over n. And these things cancel out nicely, plus 1 over n, minus 1 over n. And these two things sort of combine constructively to give exactly x over n. So left-hand side equals right-hand side. Therefore, Bellman equation satisfied. Okay. There's one extra thing if this was like an exam question and it was like, please verify that the solution to the problem is x over n. There's one thing we didn't do. We forgot to do. We've sort of done like half of it. Yeah. Yeah, the boundary condition. So we've checked that the like equation is satisfied at all the x values in the middle. Are the boundary values satisfied? So the last check is v of 0 is 0 over n equals 0, and v of n equals n over n, which is equal to 1. So it satisfies the boundary values at 0 and at 1. It satisfies the difference equation in the middle. That is the solution we're looking for. That's perfectly correct. One fun thing you can do, actually, before I do the fun thing, any questions? Yeah.
So you said before this is equivalent to projecting to the eigenvector?
This is equivalent to saying find the eigenspace of eigenvalue 1. There's 3 eigenvectors of eigenvalue 1. And we're finding what linear combination of eigenvectors of eigenvalue 1 satisfy these.
It's different than projecting.
I mean, okay, if you project onto the space of things that satisfy this, then it's the same. So yeah, it depends on how you look at it. Yeah, I think the right way to think about it is you're looking for the right linear combination that satisfies the boundary conditions. Yeah, good question. Okay, here's a fun thing you can do. There's a couple different ways you can extend it. So one is, let's see, where's my thing? Try closing it. That's not it. Oh no. Now we have to dig through all of these different things. Okay. Untitled 129, that's probably it. Hey, okay, great. So here's a fun, if you're looking for some fun things to do this weekend. This week, instead of p equals 0.5, what if we make a different p value? Let's make p equal 0.4, and then we want to say that your chance of going right is p, and your chance of going left is 1 minus p. So when p equals 0.5, you get exactly the thing we did. What happens when p equals 0.4? What does that look like? So it's now you have a 60% chance of walking towards the cliff and a 40% chance of walking towards the house. What is the answer now? And again, you can do the same kind of thing and see what does it do. And this time it gets closer, it converges to something, but the something is no longer a straight line. What function is it then? You can try to think of what function is it. It's a little bit more complicated and it has a nice curve. Okay, that's one thing you can do. Another thing you can do is you can, with the same matrix, so let's go back to the 50-50 case, 0.5, p and 1 minus p, m, rewards. You can ask different questions. So here's one thing we can ask. What if I make 0 and 0 the ends? And what if I make the rewards, what if I make them all 1s except for at the ends? So of 0 equals 0, and the rewards of n equals 0. So this is the vector we've seen a few times now. Rewards ongoing. 0, 1, 1, 1, 1, 1, 1, 1, 0. And then if I do value iteration, now I will get some other solution. But it's nice to look at. So it starts out like this, right? So my first guess is it's all zeros, and then it's kind of like building up. It's building up, and it is kind of making a nice little arch. Nice little arch. Let's see. So this is a nice looking function, nice little archy looking function, and it has the property that at the position 5, it's equal to 25. At the position 4 and at the position 6, it's equal to 24. At the position 3 and the position 7, it's oh well. Let's see. Let's see what it converges to. Yeah, at 3 and 7, it converges it's still going up, but at 3 and 7, it's equal to 21. At 2 and 8, it's equal to 16. So it's a nice function. Can anyone guess what function this is? Yeah.
It's a parabola.
Yes, it's a parabola. So it's the product of how far you are from the left with how far you are from the right. So there's again, you can prove that it satisfies this by plugging it into the Bellman equation. There's lots of nice nice reasons it should be a parabola. So this is saying if you're in the middle, it takes you on average 25 steps to fall to either side. If you're like 2 steps away, it takes you only, I guess 2 times 8, 16 steps to fall to the side. If you're 1 step away, then it's 9 steps to fall either way. Okay, so that's the Drunkard's walk. Any questions or comments about the Drunkard's walk? Okay, one thing I was going to do that maybe I will save for another day is I was going to do the 2D Drunkard's walk. And this was going to show you some tips and tricks in NumPy. But if you do the 2D Drunkard's walk, let me just scroll down to the end, you can also get a graph like this. And so this graph is, what is the 2D Drunkard's walk? Well, instead of having a house on the right and a cliff on the left, imagine that you are a drunk man who lives in a 2D plane, and you can go up, down, left, or right. So now you're walking around drunkenly, but in a plane instead of a line. And the cliff is now, or I should say it's like this. The house is this edge. So if you make it to this edge, you're safe. And then the cliffs are all around you on the other sides. So I guess it's a harder game than before. So there's cliffs all around you, and your house is only on one side. But the good news is your house is that entire edge. So if you make it to the top edge anywhere, then you are safe. And you can do the same kind of thing, and you can solve it. And you get this beautiful looking graph that looks like this. Can I make the graph bigger or nicer? Right, okay, we said the secrets are, the secrets are you close this, no, you press this button, and then you press Apple F. Nope, you press FNF. Okay, so you get this beautiful graph that goes from 0 to 1, and it has this smooth thing over here that looks like this. Why is it? Okay, there we go. So something like that. And you get this nice graph. It turns out in this case it's converging to a PDE, which is the Laplace equation. So you use the Laplace equation on a square. If you've taken PDEs, you might recognize it. And if you start really close to the top edge, then you're quite likely to get home. If you start somewhere in the middle, if you start exactly in the middle, you should have a 25% chance to make it to the top by symmetry. But your probability drops off quite quickly. So if you start like near one of these cliffs, you're quite likely to fall off the cliff before you make it to the top. Okay, the solution is exactly the same as what we did, except you just have to make it 2-dimensional. The only hard part is the programming. Maybe I'll post some notes about how to do that. Later in the course, we're going to do harder problems like this. But I guess for conceptual understanding, if you understand the 1D case, you understand the 2D case as well. Questions or comments? All right. The reason I'm skipping over this is I want to get to the next fun thing. Is so far in the course, we have only done snakes and ladders, and we've done this drunk guy walking around. These are all situations where you have no actions. So today, we're finally going to start looking at the situation where what happens when you have actions. So we're going to sort of add in actions, which are the exciting thing to sort of do. Like everything up until now, nobody has had any agency, right? The drunk guy is just walking around randomly. What if the drunk guy can make a choice? How could he choose the best choices to make it to the house? I guess the don't go to the bar and drink. Okay, so how do we add in choices? We add in choices, and in this course, choices are called actions. They're called actions. That's the thing that they are called. And so up until now, we've had a Markov chain, and then we had a Markov reward process, and we're going to add in actions, and it's something called a Markov decision process. A Markov decision process. I think I spelled decision wrong. Probably I also spelled process wrong. Decision, okay, whatever. And so before, we had these states. We had S0 was the state of time 0. S1 was the state of time 1. S2, S3. This is what you simulated in your homework, question 3. And we also added in these rewards. And we were like, oh, on the way between S0 and S1, you get the first reward, reward 1, and reward 2, and reward 3. And we had 2 types of Markov properties, right? We had a Markov property for states, Markov property for states, which says that the probability that you're in state S prime, given that you're in state S one step earlier, and a bunch of other stuff at the earlier times equals S earlier. It only depends on where you are at the previous state. So sort of anything you did in the past is irrelevant. The only thing that matters is where you are now. That's the only thing that determines your future. And we had that for rewards too. And for rewards. So it's the probability that the reward you get at time t equals r. Actually, it's joint with the state. So the reward and the state together. I guess we can, all right, let's just write it again. St equals s. St minus 1 equals s old. That is equal to the probability only given okay, so that's what we had before, and there were no actions. And now we're going to add in one new ingredient, which is the actions. So instead of having the sequence S0, R1, S1, we're going to add in an extra thing, which is called the actions. The action at time 0, the action at time 1, the action at time 2. So it's like a sequence of 3 types of things. You're at some state, you choose some action, you see some reward, and then you end up at some new state. Then you repeat the process again. So the AIs, the A or the ATs, let's say, they are actions, and they are chosen from an action space. An action space. And we're going to do fancy A for the set of all possible actions. And actually, sometimes the actions depend on the state you're in. So AT actually is sometimes in A of ST. So when you're in state ST, you have some number of options available to you, some set of actions, and you choose one of them. That's what you do. And once you've chosen the action, given the state you're in and the action you are in, the action you've chosen, that should determine everything else that comes. So the Markov properties for states and for rewards, they get updated. So they get updated to depend on the action. Depends on the action. And the where you go and what rewards you get can depend now on the action you get. So the only thing we're going to add is on the conditional side. We say, given the action you chose is action A, there is some, there's some action A that determines what it is, and it gets added to the right-hand side here of the given. And when you choose the action, that determines the distribution of where you move in the next time step and the set of rewards you get. So the Markov properties still work, and now instead of depending on just what state you are in, it depends on the state and the action you are in. And the big question we are going to try to answer in this course, and this is like what reinforcement learning is question, how do you choose the actions to maximize your reward? Your reward. So up until now, we've been just calculating the rewards, right? So we've been saying like, okay, you're in this situation, you're the drunk guy, what is the chance you end up over there and you end up over there? But now we're going to say, okay, now imagine you're the drunk guy and you can pull these levers to have different things happen to you. How do you arrange things? How do you make the best choices to maximize your chance to end up at the house, right? That's the kind of thing we're going to do. So that's like the definition. Yeah, very formally speaking, what the definition is. As we see examples, I think it'll make more and more sense. But are there any questions or comments about the definition so far? Okay, so, and the very first example we're going to do, I tried to pick a fun one. So the example, it is a dice game called Pig. The dice game Pig. Okay. Who has heard of Pig before? Pig. Okay, almost nobody. That's good. That's fine. We're going to watch a video and see what Pig is. Okay. That was here. Where was it? Untitled thing. Okay. Okay, so this is another number file video called The Math of Being a Greedy Pig. And we'll start it here. Let's pause there. Are the rules of the game clear? So you roll the dice. You can choose, if you're greedy like Brady, you roll until you get a 1 and then you get 0 points. And if you're wise like Ben, you can stop rolling, and when you stop rolling, you bank the points you have, and they get added to your total. it flashed on the screen for like 1 second. That first to 100 wins. So you're trying to be the first one to get to 100 points, taking turns. Any questions about the rules? Okay, so I brought some dice in the last 10 minutes. You guys will play the game. This is going to be our first example. So I want you to think about how are we going to fit this into our framework? Like, what are the states, the actions, and the rewards? So I'll let you guys play it. Let's play first to 50 points. So pick somebody next to you, partner up, and play first to 50 points, and try to think of like first of all, how do you model it? What are the states, actions, and rewards? And second of all, like what is the optimal strategy? Like what does it mean to choose actions that maximize your rewards? Okay, get in your final answers in here. Take your final guesses, and then we will reveal and see what people are thinking. Well, I guess I'll have it keep beeping until people answer. Okay, I think there's one person maybe who hasn't gotten in yet. Let's see. Okay, reveal counts. So the set of actions are, some people said roll again or bank, roll stop, roll or don't roll bank, roll again or no. Yes, this is all perfectly correct. So at every given point, you have two choices. You can either roll again or not. It's like kind of a very simple game where the action space is one of two things. Of course, as the games get more complicated, you can imagine the action space could be very large or continuous or whatever. But for this game, you have two options at every point. So good consensus on that. Very nice. And yeah, so when we set this up properly as a Markov decision process, we're going to have the state, and then you're given the state, and you choose roll again or don't, and then you see a reward, and you move to the next state. That's what's going to happen. Yeah. Okay. Yeah.
With this game, isn't there a rule where if you roll one right off the bat, you lose all your points entirely?
Yeah. I guess in the way we're playing right now, if you roll a 1 at the beginning, you get $0. That's which didn't that happen to Brady one time in the video? I think, or was he always greedy? Right now, the way we're playing, if you roll a 1, you start at $0. You could imagine an alternate version of the game where you get like one freebie or something, right? But in our version, right? So as written in the question, you get $1 per banked point you have at the end. If you roll a 1 in your first round, then $0 for you. Have a nice day. That's it. Okay. So roll again. The actions are quite simple. What is the state space? That's actually kind of tricky. Let's see what you guys said. So kind of tricky. Lots of people said 0, 1, 2, 3, 4, and one brave soul is in something else. The correct answer is, of course, something else. Something else. So it cannot be this. If you think about it carefully, this on its own cannot be enough. And last but not least, let's see, what did you guys say for the types of rewards? Again, most people think there's ongoing rewards, but actually I claim the easiest way to set this up is there are only terminal rewards. Okay, so in the last 3 minutes, we're gonna go into all of this in detail, but let's focus on why can't it be 1, 2, like it cannot be only 0, 1, 2, 3, 4. So yeah, the 0 has to be there for the starting square, but there's something else that is missing from this set. So I'll let you guys think for a minute, and then let's nail down what is the thing that is missing from this situation. Why can't it just be 0, 1, 2, 3 on its own? Okay, you guys think for a minute, and then we'll take it up in a minute. We'll chat about it, and then we'll do even more pig next class.
As in the dice structure. that corresponds to what the value is. And
Okay. Can anyone think of why you need to do something else other than 0, 1, 2, 3? Yeah.
You need to tell if the game ended.
You need to know if the game ended or not. So if you have these states 0, 1, 2, 3, you can use those to keep track of, okay, you're at 3 and you're still playing, but you need some kind of way to determine, is the game over? And so one very simple way is you could do 0, 1, 2, 3, and you could have one extra state that's like the I'm done state. But it's actually more convenient to think of having two copies of 0, 1, 2, 3. You have 0, 1, 2, 3 with you're still playing, and you have 0, 1, 2, 3 with and you're done. So kind of the state space for this game, we'll set it up next class, and so it will formally be like this. The set of states is actually split into two, and there's the done row and the still playing row, and they both kind of go on forever. Still playing and done. We are going to go into detail about this last time. You can technically set it up with just one single done state, but you'll see that it's more convenient to do it this way. That's what we're going to do next class. Any last minute questions or comments? Yeah.
Can you not get state 1?
Yeah, it's true, but we might as well include it in our thing. So yeah, once again, you can do like some optimizing and like delete state 1. When you implement it on the computer, it's very convenient to have state 1 so that state S corresponds to having S points. Otherwise, you have some like weird like off by 1 thing that you can't forget. Okay. All right, great. So we'll meet on Thursday.